Hello students. So in the previous lecture we have studied the integrated rate law for the zero order reaction. So in the today's lecture we are going to study integrated rate law for first order reaction. Okay. So now here we will assume reaction A gives the product P. So now rate is equal to minus dA upon dt. Okay. So for this reaction rate is equal to K into concentration of reactant. Here the reactant is A. Here we have assumed that the reaction is first order. Therefore, the order will be equal to 1. Okay. Now we will continue this minus dA upon dt is equal to K into concentration of A. We will shift this dA upon, we will shift this concentration term to the denominator and this dt to this side, K dt. Okay. So now we will shift this minus sign to this side. dA upon concentration of A into minus K dt. In the next step, integrating on the both side. So now integration of dA, so the integration limits will be A0, where A0 is the initial concentration of reactant to AT. That means AT is concentration of reactant at time T. Okay. Concentration of reactant at time T. So this minus K dt. Here integration limit will be from 0 to T. That is from 0 time to some time T. So now integration dA upon concentration of A from A0 to AT. This minus sign we will take outside the integration sign. K is constant. It will also come outside integration from 0 to T dt. Okay. Now we know that integration of dx upon x is ln of x. Okay. Similarly, integration of dA upon A will be ln of concentration of A, and the integration limit will be A0 to A t. Okay. Now minus k, integration of dt is t from 0 to t. Okay. Now putting the limits of integration, ln of at minus ln of a naught, which is equal to minus kt. Therefore, kt will be equal to minus ln of at minus ln of a0. So when solving this bracket, it will be ln of a0 minus ln of at. Due to this minus sign, it will be get revert kt. We know that ln of a minus ln of b is equal to ln of a naught upon at. Okay, which will be equal to ln of a naught upon at, which is equal to kt. So therefore k is equal to 1 upon t ln of a naught upon a t. Okay. We know that ln of x is equal to 2.303 log of x. Okay. So therefore k is equal to 2.303 upon t log of a0 upon a t. This is the equation, or this is the rate law for first order reaction. Okay. So our equation was k equal to 2.303 upon t log of a naught upon a t. Okay, is this clear to you now? So now next form of this equation will be 2.303 upon t log of a upon a minus x, where a is the initial concentration of the reactant and x is the concentration of reactant at time t. So we will see half life time of first order reaction. So half lifetime of the reaction means the time required to convert half of the initial concentration of reactant into the product. So now K is equal to 2.303 upon T to log of A naught. So to find half lifetime, that means to convert the reactant into half, or to convert the reactant into half of its initial concentration. So half of its initial concentration, that means A naught upon 2. So therefore 2.303 upon T is equal to log of 2. Why? Because this gets cancelled. So now log 2.303 into log 2 value is 0.3010 upon T, which is equal to 0.693 upon T. So therefore T half, that is half lifetime of the first order reaction, is 0.693 upon K. So here you have to remember one thing, that the half lifetime of the first order reaction does not depend on the initial concentration of the reactant. Okay. So next we will see the graph. First, log of A0 upon AT versus time. So our equation is this: K is equal to 2.303 upon T into log of A0 into AT. So that means that graph will have no intercept. Okay. First of all, that graph will have no intercept and it is a straight line. Straight line having a positive slope, having no intercept, that means passing from the origin. Okay. Is it clear? This will be the nature of the graph. Next is concentration versus time. So to find the concentration versus time, we have to rearrange that equation. That equation is K is equal to 2.303 upon T log of A naught upon AT. So now log of A naught upon AT, or we also have the another equation, that is K is equal to 1 upon T ln of A naught upon AT. So now we will shift this ln of A naught upon AT, which is equal to KT. Okay. So now ln of AT upon A0. So we have taken the reciprocal, so which will be equal to minus KT. So when this ln shifts to this side, it becomes e raised to. It becomes e raised to minus KT. Okay. Therefore, AT, that is concentration at time T, will be equal to A naught into e raised to minus KT. And that graph will come like this. concentration versus time. It will be exponential curve. Okay. So this was about the integrated rate law for the first order reaction. So now next we will see the integrated rate law for the second order reaction. So here assume the reaction A gives the product P. Assume that the reaction is second order reaction. So assuming that reactant are same. So now rate is equal to minus dA upon dt, which is equal to K into A raised to 2. Why 2? Because we are assuming that the reaction is second order reaction. So minus dA upon dt is equal to K into concentration of A square. So now minus dA upon A square, we have taken this concentration term to the denominator and this minus will shift to this side, K dt. Now integrating on both the sides, integration from A0 to AT, where A0 is the initial concentration, AT is concentration of reactant at time t. dA upon A square, which is equal to integration minus K dt from 0 to t. So we know that integration of dx upon x raised to n is equal to we know that integration of x raised to n dx is equal to x raised to n plus 1 upon n plus 1. You have to remember this formula. So now this integration of dA upon A raised to 2. So integration of A naught to AT A raised to minus 2. Why minus? We are shifting it from denominator to numerator. dA. And this integration 0 to t minus k dt. Now integration of this will be equal to concentration of A minus 2 plus 1 upon minus 2 plus 1 and limits from A0 to AT. Okay, this integration will be minus k t. Okay, so this minus 2 plus 1 will be minus 1. So this minus sign outside, A raised to minus 1 A0 to AT is equal to minus KT. So this both minus sign gets cancelled. Now AT raised to minus 1 minus A0 raised to minus 1, which is equal to KT. So this minus 1 we can write like this, AT minus 1 upon A0, which is equal to KT. Okay? Are you understanding this? So therefore, K is equal to 1 upon T into the bracket 1 upon AT minus 1 upon A0. So this is the rate law or integrated rate law for the second order reaction. Okay? So now we know that K is equal to 1 upon T 1 upon AT minus 1 upon A0. This is the rate law. So now for finding the half life time required to convert the initial concentration of reactant to the half. So at half life, that means at AT is equal to A0 upon 2. So K is equal to 1 upon T 1 upon A0 upon 2 minus 1 upon A0. So 1 upon T, which is equal to 2 upon A0 minus 1 upon A0. So what we will do? We will take this A0 common. That is 1 upon T to A0. In the bracket remains 1, 2 minus 1. So therefore K is equal to 1 upon T into A0. So therefore T1 half is equal to 1 upon K into A0. So half life time for the second order reaction depends on the initial concentration of the reactant. Okay? Is it clear to you now? So next we will see the graph of second order reaction. So in the graph, that is 1 upon concentration versus time. Okay? And that graph comes to be equal to like this, where intercept is equal to 1 upon A0. Okay? So how we have found this? See, K is equal to 1 upon T into 1 upon AT minus 1 upon A0. Okay? So KT is equal to 1 upon AT minus 1 upon A0. That means Y is equal to mx plus C. Okay? So instead of writing like this, T is equal to 1 upon K into 1 upon AT minus 1 upon K into 1 upon A0. So therefore time, that is y, is equal to mx plus c. So slope will be equal to 1 upon k, and intercept, that is c, will be minus 1 upon k into a nod. Okay. So now we will stop here. Thank you.